Welcome to Getting Started with Calculations in Tableau. Similarly to formulas in Excel, calculations allow you to manipulate your data in any number of ways. Creating a calculated field is as easy as right-clicking in the data pane and selecting Create Calculated Field. Functions in Tableau fall into one of several main categories: number, string, date, etc. Calculated fields are created by defining a formula using these functions or basic operations. Let's create a simple logical calculation on our profit field as an example. If sum of profit is greater than 0, then positive, else negative, end. I'm ignoring if profits are actually 0 for simplicity's sake, and we'll name this sign of profit. Note that there's an equal sign in front of the field here. This indicates it's a calculated field, not natively from the data source. If we bring this calculated field to color, we see that our profit bars are colored appropriately. If we want to see what our costs are, defined as sales minus profit, we can add that to the view very simply by double-clicking and typing it directly into the shelf itself. Note that autocomplete pops up as I type, and I can hit Enter to select. We can also drag in a field from the data pane and hit Enter. And there we have the calculation's results visualized, and we have a new pill with our formula. If this is a calculation that we find useful and want to keep, we can simply drag the pill into the data pane, and we can always rename the field if desired. While learning about how Tableau handles calculations, a really important concept is the distinction between regular calculations versus what we call table calculations. A regular calculation, such as sales minus profit, is passed as part of the query that Tableau asks of the data source, and the computation is handled by the data source itself, with only the result set being returned to Tableau. A table calculation is a secondary calculation that is performed on top of the returned result set. This computation is done within Tableau. An example here is running total of sales. A table calculation is indicated by the delta symbol on the pill. Table calculations can either be written like any other calculation, using the table calc functions in the calculation editor, or there is a set of predefined, commonly used computations called quick table calculations. These include options like running total, percent of total, and year-over-year growth. Which ones are available depend on the data in your view. Calculated fields are created by defining a formula. The formula is composed of built-in functions or operators and fields from the data pane. Let's right-click on the if calculation and select Edit to take a look. The right-hand side of the calculation editor provides information about the functions. It can be collapsed to save space or expanded. If we select the logical category, and then if, we see information on how to use the if function. We need to say, if something, then what to do if it's true. We could add an else if with another expression for evaluation, and then what to do if that expression's true, followed by an else, which is a final condition if nothing else has been true, followed by an end. Let's create a simple logical calculation on our profit field. Right-click in the data pane and select Create Calculated Field. We'll name it Profit Cutoff. First, we'll type if. Note the autocomplete coming up as I type. Down here, we see the calculation contains errors. We can ignore this for now because we're not done, but it's a good idea to keep an eye on this indicator as we build our calculations. Next, we'll type sum with an open parentheses. This is because we want to aggregate the measure so our results are computed correctly regardless of the structure of the view. For more information, see the Aggregation, Granularity, and Profit Ratio video. Aggregations are color-coded light blue in the formula. Here we can either type in profit or drag the field in from the data pane. Field names are coded orange in the formula. Note the square brackets. This isn't necessary for a single word field name, but if we were using a field like shipping cost, we'd need those brackets because of the space. We'll close the parentheses to wrap up the aggregation sum. Now let's think about what we want to show. If profits are over $150,000, we want to call those subcategories high profit. To write this in a calculation, we'd use the greater than operator and then our value. Greater than 150,000. Standard operators like addition, multiplication, and comparisons like less than or equal to are supported in Tableau. We need to tell the calculation what to do if the condition of greater than 150,000 is met. We want it to call those marks high profit. We do this by saying, then high profit. Then does not need to be in all caps, but it can be a good habit to get into. And note that the words themselves must be set off in quotes to let the calculation editor know that they are text. We also have to specify what will happen if the condition is not met. Else, not high profit. We see the indicator at the bottom says that the calculation still contains errors. Clicking on the indicator gives us more information. Ah yes, an if statement needs to end with end. Add that in, and now the calculation is valid. We'll hit OK. If we bring this calculated field to color, we see that all the bars above our reference line are color-coded high profit, and anything that's below is coded not high profit. Table calculations are performed on the returned results of a view. Here we have the sum of sales broken out by category. What if we wanted to see the percent of total instead of actual sales values? Right-click on the sum of sales pill and select Quick Table Calculation. Then percent of total. We can now see those values were converted into percentages, and technology is about 37.5% of our overall sales. Table calculations are computed locally in Tableau, rather than being handled in the database. The calculations are based only on the information in the view. This is sometimes referred to as the field set. In a given view, the underlying data table, hence table calculations, contains the information that makes up the marks. If you're working with a crosstab, this data is exactly what you see. For any other view, the underlying data is represented differently, but the values are the same as the crosstab. This data table, which comprises all fields used to define the view, is called the field set. For this particular view, the field set consists of category, segment, and quantity, all of which define the breakdown and length of the bars in the view. Altering the view by adding or removing fields changes the field set, which in turn alters the table calculation. Many common calculations are treated as table calculations in Tableau. Quick table calculations are easy, one-click options that can be applied to a given view. For example, what if we want to ask about our running total of profit over time? Here we have month of order date and profit in the view. We can add a quick table calculation by right-clicking on profit, selecting Quick Table Calculation, Running Total. And we see a pretty steady growth in profit. Great! If we think we'll want to use this regularly, we can drag the pill with the table calculation over to the data pane to save it as a calculated field for easy reuse later. Table calculations can also be written in the calculation editor like any other calculation. Usually, this would be done with table calcs not available as quick table calcs, but to compare, let's recreate this running total by hand. Right-click in the data pane and select Create Calculated Field. We'll name it Running Sum. If we change the function type to Table Calculation, we see the long list of options for table calculations. Again, these functions are performed on the field set that makes up the view. We'll pick Running Sum, and if we just type profit, we get an error. We need an aggregation. Remember, in the view, we did our quick table calculation on the sum of profit pill. We need to specify the aggregation when manually writing a table calc. Wrapping profit in sum clears up the error. And if we bring this calculation to the rows shelf, we see we get the same result as the quick table calculation. Here, we have the running total of profits by month. Let's ask a new question. At the level of monthly profits, has technology had the highest running total of profits each year? To answer this, we need to modify the view and the table calculation. We'll add discrete year to columns and bring category to color. But this is a combined running total from 2012 to 2015. I want it to be a unique running total per year. Because of the question we're asking, we have to modify the way the table calculation is being computed. Right-click on the pill and select Compute Using. Here are several options for the scope and direction of how the calculation should be computed. But to see better what these options mean, let's instead choose to edit the table calculation. Now, as we click through the options, we can see what changes. Tableau has defaulted to have the calculation run along table across, meaning we see the running total of profits across all 4 years. But we want to know if technology had the highest running total each year, so we want to look at each year independently. Changing the scope from table to pane gives us this calculation, computing the running total for each pane or year. And it looks like technology did have the highest running total of profit each year. We saw that table across and pane across provided different interpretations of the field set by using a different scope. For our data, the direction, across, down, etc., doesn't matter, as this is a fairly simple arrangement. A great way to see the distinction between combinations of different scopes and directions is to use the percent of total calc on a crosstab of numbers. Here on the Scope and Direction dashboard, the subtotals for each combination of direction and scope are slightly different and allow for different questions to be answered. You may want to pause this video and explore the dashboard, as we will not go over it. If altering the scope and direction of the table calc doesn't give the results we're looking for, we have even more control over how the calculation is computed by referencing specific dimensions. All dimensions in the view will be used in a table calculation, either for partitioning or addressing. Partitioning fields scope the data. They define the groups of data the table calculation is performed on, like using pane to partition our data by year earlier. Addressing fields are any dimensions not used in partitioning, and they determine the direction of the calculation. The order of addressing fields also matters. Here we have the percent of total sales broken down by category and subcategory. To see which fields have been categorized as addressing or partitioning, we can edit the table calculation. We see that the scope and direction is table down, and the partitioning and addressing fields are automatically determined by this selection. However, if we want to change these ourselves, we simply need to select specific dimensions. In this list box, we see that both category and subcategory are checked. Anything checked is addressing the data. Let's uncheck both, making them partitioning fields. Now every percent of total is 100%, because the calculation is running on the partition of subcategory and category, so each is 100% of itself. If we only check subcategory, we're now partitioned by category and addressed by subcategory. and we see the breakdown within each category as a distinct unit. We can see, for example, that phones make up almost 36% of the sales in technology. If we check both subcategory and category, making them both addressing fields, we're back to being table scoped with no partition, and we see that phones are only 13.5% of the overall total across all categories. In this example, it doesn't matter if category or subcategory is at the top of the list box. But the order can matter, as it controls the order in which the calculation is run. We can drag fields to change the order. Check out the online help for more information. Because table calculations can be set to calculate at odds with the visual arrangement of the data, or in a view that's not as immediately understandable as a crosstab, it's important to understand what's going on when you select a compute using option or determine the addressing and partitioning fields with specific dimensions. Level of detail, or LOD expressions, allow us to easily compute aggregations that are not at the level of detail of the view. Let's say we want to see average profit per country. Here we have a map colored by average profit, and we can see that Argentina has an average profit of -$48. But what does that actually mean? If we click to bring up the tooltip buttons, go to View Data and the Full Data tab, we see that more often than not, there are multiple line items for a single order. Now we understand what the map shows. The average profit for country is the average profit of all the line items in that country, which is the granularity of the dataset. But is that what we want? Wouldn't it be nice if we could find the average profit of all the orders within the country, even when there are multiple line items in an order? In other words, can we aggregate up to the order level to compute the profit? To find the average profit per order, two things need to happen. First, we must sum up the profit for each order ID. Then we need to average all of those values for each country. First, we want to sum the profits per order. This is exactly where a level of detail expression is useful. The expression looks like this. Include order ID, sum of profit. That is, we want to roll up all the line items to their order ID when we're computing the sum of profit. We'll go over the syntax in more depth in a moment. Just remember that this expression sums up the profit for each order ID. Now we want to average those values for each country. We take care of that in the view itself. We'll bring profit per order ID to color, and we need to change the aggregation to average by clicking on the pill, going to Measure, and choosing Average. We see that the average profit per order in Argentina is -$98, substantially different from the -$48 we saw before. In fact, let's see the two calculations side by side. Here we see all of the countries. On the left is average profit of all line items within each country, like the first map. On the right is the average profit of all orders within those countries, the LOD expression from the second map. Both sets of blue bars show an average, but the averages have been calculated at different levels of detail. The level of detail on the left is country, and the level of detail on the right is country and order ID. Notice that we have not added order ID directly to the view. Our original question was about the average profit per order by country. The LOD expression itself gave us the profit per order. The country field in the view broke those totals out by country, and the average aggregation on the pill averaged the values. Now that we've seen what LOD expressions can do, let's take a moment to review the syntax. Right-click on Profit per Order ID and click Edit to bring up the calculation editor again. LOD expressions are enclosed in curly braces. The first piece inside the curly brace is a keyword, either fixed, include, or exclude. After the keyword, we enter the dimensions that the keyword will act on. Fixed computes the value using the specified dimension without reference to any other dimensions in the view. Include computes the value using the specified dimension in addition to whatever the dimensions are in the view. In our example here, we included order ID in the LOD expression along with the dimension in the view, in our case, country. The last keyword option is exclude, which will ignore the specified dimension even if it is used in the view. Next, enter a colon. This tells Tableau that we're done declaring the level of detail and are about to enter the aggregate expression. Finally, the aggregate expression itself. This is usually what we want the calculation to do, such as give us a minimum order date or an average discount. In our example with average profits per country, we could have used fixed instead of include if our order IDs were unique worldwide. Because order IDs in our dataset are unique only per country, with some order IDs used independently in multiple countries, fixed and include will give different results in this setup. Why is that? Fixed only cares about order ID. Therefore, it sums profits from orders occurring in multiple countries. Fixed is going to count France's negative $8 order ending in 051 against Belgium's sum of profits, because that order ID was also present in Belgium, and fixed cares only about order ID. In contrast, include looks at both order ID from the LOD expression and country from the view, so it treats France and Belgium's versions of the 051 order as separate and only considers the value for Belgium when displaying the profit for Belgium. So the value here for include is higher by $8 than it is for fixed. If the order IDs were globally unique, like the bars on the left, fixed and include would have the same results. To look at it another way, with order IDs not globally unique, fixed ignores the country dimension and takes the sum per order ID. Include breaks the order down based on how the view is structured, therefore by country. If we add the two values for include, we see they sum to the value given by fixed. Have you ever seen an AGG at the beginning of a pill? AGG stands for aggregation and tells us that the aggregation is built into the calculation rather than performed after the fact. Let's create a profit ratio to see this. Double-click in the columns shelf, and we'll type sum of profit divided by sum of sales. Notice that the pill now begins with an AGG instead of the usual default sum. This means the aggregation is part of the calculation itself. We know what AGG means, but what about ATTR? This is another common thing seen with aggregate calculations. Let's say we want to aggregate separately for different dimension values. For example, we want to average corporate sales, but take the median sales of the other customer segments. Right-click in the data window and create calculated field. We'll call this segment sales. And we'll say, if segment equals corporate, then average sales, else median sales, end. But Tableau tells us there's an error in this calculation. We cannot mix aggregate and non-aggregate comparisons. So we need to aggregate segment, but how? By using the attribute aggregation. We'll wrap segment in ATTR. And don't forget the parentheses. Now the calculation is valid. When we add segment sales to the view, we can see that the average corporate sales are much larger than the median sales for other segments. And now we know that this pill says AGG because the aggregations are defined in the calculation. But what did attribute actually do? Attribute checks to see if there's only one value for a given field for all rows in a result set. If there's only one value for the data selected, attribute returns that value. If there is more than one value for the subset of data, it returns an asterisk. Another way of thinking about the attribute function is as the equivalent to the logical test, if min equals max, then return that value. We could also use min or max if we know there's only one value, although these may artificially pick a single value when there are many values that could be there. But all of these aggregations are useful for aggregating dimensions to get around the errors like the one we saw. Finally, what about aggregated versus record-level calculations? Let's look at the average sale per order. We'll start by right-click dragging sales onto the columns shelf. This allows us to choose the aggregation. We'll select Average and click OK. This is the average sale per row of the database, which consists of product-level transactions, not order level. We want to know the average of a single sale for an order, not a record-level average. To do this, we'll create a calculated field. Right-click and select Create Calculated Field. We'll name it Average Order Sales. And averages are calculated by summing a set of values, then dividing by the number of values. So we'll do sum of sales divided by the count distinct of order ID. Now we'll bring average order sales to the columns shelf. We can see that these values are larger than the average sale value, which makes sense because we're taking the average of values summed to the order level rather than the record level. A common question in analysis is how long did something take? We can easily create a date calculation to tell us. Here we want to know the average time it takes for an order to ship for each country. Let's right-click in the data pane and select Create Calculated Field. We'll call this Time to Ship. We'll use a date function called dateDiff to get the amount of time between order date and shipping date. The dateDiff function needs to know what date part we want to consider. We'll use day. Note that the date part needs to be lowercase, in single quotes, and singular. We also need a comma. Next, we'll bring out our start date, or order date, followed by another comma, and our end date, or ship date, and close parentheses. We see this calculation is valid, and we'll click OK. Let's color our countries by using time to ship. We'll change the aggregation to average, and we can edit the colors to a red-black diverging palette. And we'll reverse it because more time is bad. Now we can quickly see the countries with the longest shipping times, and we can focus on those areas. Tableau works very well with dates once it recognizes the data is a date. However, in this dataset, our dates aren't in a common format. We have our dates stored separately as day, month, and year. We want to create a calculated field that combines these three fields into one that Tableau can recognize. Right-click, Create Calculated Field. And we'll name this Tableau Date. In the calculation editor, we'll use the MakeDate function. The MakeDate function lets us combine separate fields into a date by simply dragging out the pieces in the right order. We'll bring out year, and a comma, then month, and a comma, then day, and close parentheses. The calculation is valid, and we'll click OK. Now we have a date that Tableau can recognize. And we have the full drill-down capabilities that we expect. A logical calculation determines if a certain condition is true or false, also known as Boolean logic. Here, we want to know if our countries are performing well. Countries fall into markets, and some of our markets are considered emerging and some are not. We want our end user to be able to determine what the cutoff is to be considered a well-performing country, depending on which market the country falls into. We've created two parameters. We can right-click and edit to see how they're set up. We also have a calculated field, Performing Countries. Let's right-click and edit. It looks complicated, but all we're doing is checking two variations on a statement. We look to see which market the country falls into, and if the sales are above threshold. Two markets are considered emerging, so they're compared against the emerging threshold. Three markets are not considered emerging, so they're compared against their relevant threshold. And if none of these statements are true, the calculation returns underperforming. We can use this field on color to easily see which countries are considered well-performing based on the thresholds. As we change the parameters, we change the thresholds and alter the analysis. A conditional filter is a filter that keeps or excludes members based on a logical calculation. Let's say we only want to see a specific subset of countries. Particularly, we want to see those that have at least $200,000 in sales and have sold at least 1,100 distinct products. Mexico will fall into this category, as it has sold over $620,000 in sales and over 1,300 distinct products. India will not, because it does not meet the product cutoff. Sifting through this manually would be difficult, so let's create a filter based on a condition. We'll bring Country to the Filter shelf and click to the Condition tab, where we can enter our own formula. We simply want to check if the sum of sales is greater than 200,000 and if the count distinctive product ID is over 1,100. When we return to the view, we see only true values returned, countries that meet both of these thresholds. Let's say we're responsible for the sales for several brands of products. If we look at product names, most contain the company who makes them. We want to highlight and focus on the ones that we're in charge of. To do that, we can create a list of those companies and then create a calculation that finds product names containing those companies. We have a parameter already set up. Let's right-click and edit. And we see that it's a string parameter that allows a list of values. These values are the companies we're interested in. We'll add one for Xerox and click OK. Now we need to create a calculation that checks if one of these names is in product name. We'll right-click in the data pane and select Create Calculated Field. We'll call this Company Products. We'll use a string function contains to find out if the company name we have selected in the parameter is found within the name of the product. We'll type contains, and we're first asked for the string we want to search in. This is product name. And we need a comma. Now we're asked for the string we want to search for. In this case, it's the company name from the parameter. So we'll bring that out and close the parentheses. The calculation is valid, so we'll click OK. We've now created a Boolean, or true-false, calculation that we can use in the view. We'll bring this field to the filter shelf and keep only true. Now when we click through the parameter, we see products from the specific companies that we're interested in. A common need is to split a field into separate parts. In our dataset, Order ID consists of 4 parts: the distribution center code, the year of the order date, and 2 additional pieces to make it a unique identifier. Let's split these into separate fields. We'll right-click on Order ID, select Transform, and choose Split. Tableau has now created 4 new fields, one for each part of the Order ID. Let's rename the split one as Distribution Center. Let's bring this out, and then bring out number of records so we can see the volumes going through these distribution centers. As a note, splitting strings can also be done when connecting to the dataset originally. In this dataset, we have sales quotas for some, but not all of our countries. Our main goal is to compare the sales to their quotas, but we cannot compare a number to a null because null means unknown. We need to convert our nulls to zeros so that we can do a comparison. Right-click in the data pane and select Create Calculated Field. We'll name it Corrected Quotas. And we'll type ZN with an open parentheses. The zero null function returns a zero wherever there's a null. We can think of this function as asking, is there a quota for this country? If not, give it a 0. We'll drag out quotas and close the parentheses. Now if we bring corrected quotas to the view, we see zeros where we had nulls before. Now we can move on and continue to analyze our data without worrying about hitting null values. So let's look at just how different our sales are from our quotas. We'll start by creating a new calculated field, and we'll call this difference. We want our sum of sales minus the sum of our quotas, and make sure to use the corrected quotas so we don't run into those null issues. Let's bring this into the view. We can now see which countries are below quota and by how much. Taiwan, Austria, and Portugal are pretty big outliers in the positive direction, because those are instances where we have a quota of 0, so the difference is pretty vast. We should probably go back and give these countries quotas. Here we're looking at a dataset of patient IDs. All IDs should be at least 3 digits long. To check this, we can use a calculation to look at the length of the IDs. We'll create a calculated field by right-clicking in the data pane and selecting Create Calculated Field. We'll call this length. For the formula, we'll type LEN and open parentheses. And then we'll drag out patient ID and close the parentheses. But the indicator shows that we have an error. Click on the error to bring up the error message. The length formula LEN needs a string or text rather than numbers in order to work. So what we need to do is convert this number to a string. This is where the type conversion functions come in. We'll wrap the patient ID in the string function by clicking in front of the field and typing str, then wrapping the whole thing in parentheses. The calculation is valid because length is applied after the string conversion. We'll click OK. We can see here that the calculation has been created as a measure, but really it should be a dimension. We'll just drag it up into the dimensions area. And now, let's bring it out into the view. Yep, it looks like we have a bunch of IDs that are less than 3 characters, so we're going to have to go through and make sure those errors are corrected. Here we have a dataset with students and their birthdays, and we want to see how old these students are. We'll right-click, create a calculated field, and call this age. We'll use the formula dateDiff to find the difference between the two dates. Here we're looking for the number of days between our start and end dates, with the start date being birthday and the end date being today. And we'll close the parentheses. Because we're counting the number of days between these dates, we need to divide by 365 to get the ages in years. The calculation is valid, and we'll click OK. Let's bring out these ages. Oh dear. Look at these decimal points. What we want is just the whole number for age. And to get that, we need to round down to the whole number. We can do this using the integer function. This will strip away the decimals, leaving just whole numbers. We can right-click on age and edit the calculation. This time we'll wrap the entire calculation in the int function. Now we get the whole numbers for our ages. You may be wondering why we didn't just use year with dateDiff. Here we have a calculation with date diff in years. Let's bring this out into the view. We see that there are instances where the ages are off by a year. This is because date diff with year simply subtracts the year values from each date instead of considering the day and months of the dates as well. Level of detail expressions extend Tableau's calculation language by introducing the capability to specify the exact level of aggregation within a calculation itself. An LOD expression is established by curly braces. The first piece inside the braces is a keyword, then the dimension declaration, followed by a colon, then the aggregate expression. Let's work through each piece of the syntax backwards, starting with the most recognizable part. The aggregate expression portion of an LOD expression should be familiar. This can be anything from a simple sum of sales to a complex calculation. Here's an example of a calculation in the aggregate expression, in this case, providing the date of a customer's second order. Note that aggregate expressions cannot contain ATTR or table calculations. The dimension declaration identifies the dimensions that define the level of detail to use when performing the aggregation. If no specific dimensions are declared, the LOD expression is considered table-scoped, which is a complete aggregate of the data. The keyword can be one of three options: fixed, include, or exclude. These keywords are very powerful, and to truly understand all the implications of using a given keyword, we recommend watching all the LOD videos in this section, as each addresses different aspects of keyword behavior. Level of detail expressions that use include or exclude keywords will always result in measures. Fixed keyword expressions will default to be dimensions or measures based on the aggregate expression. If the aggregate expression would yield a measure, the overall expression will be a measure, such as number of orders per customer. If the aggregate expression would yield a dimension, such as a string, Boolean, or date, the overall expression will be a dimension, such as second purchase. The keywords also impact where the LOD expressions are evaluated in regards to filtering order of operations. There are several kinds of filters in Tableau, and they are executed in the following order from top to bottom. If you're familiar with SQL, you can think of dimension filters as the where clause in a query, and measure filters as the having clause. Fixed calculations happen before dimension filters. Effectively, any filter on the shelf will be ignored, if it's not a context or data level filter, when computing the fixed results. This behavior is desired and necessary to make fixed behave as expected. For example, here we have a view that shows the percent of total shipping costs broken out by order priority and a breakdown of shipping costs and profit. The percent of total shipping cost is calculated by taking the sum of shipping cost and dividing by the LOD expression of a table-scoped sum of shipping cost. If we filter out an order priority, say medium, we want our percent of total to still refer to the total of all order priorities, even if we filter out the marks from the view. If the fixed LOD expression, or table-scoped here, filtered after the dimension of order priority, we wouldn't retain the overall total. Include and exclude LOD expressions are evaluated after dimension filters and before measure filters. If a calculation has a different level of detail, something needs to be done to reconcile the difference. This can be seen most easily with fixed. Fixed level of detail expressions compute values using specified dimensions without reference to the view's level of detail. Because a fixed LOD expression is independent of the view's LOD, the results may either be below, that is, more granular than, or above, that is, more aggregated than, the LOD that established the marks on the sheet. If the LOD expression's results are more granular than the view LOD, such as in this example, the values from the LOD expression are aggregated to create the view. Here, the LOD of the view is simply segment, but the LOD expression was fixed at a more granular level of both segment and category. The LOD expression's values for each category are aggregated into a single value per segment to be displayed in the view as the result. If we preemptively wrap the level of detail expression in an aggregation when we create it, Tableau will use the aggregation specified rather than choosing one for us when that expression is placed on a shelf. Here, for example, we want the average category per sale. So while we summed the sales inside the LOD expression, we want the results to be displayed as an average. This arrow diagram illustrates the process schematically, showing the value of the LOD expression computed at a lower level than the viz LOD, then being aggregated back up to be displayed at the viz LOD. If the dimension declaration is less granular, more aggregated, than the view, the values from the LOD expression are replicated to create the view. Here the LOD of the view is both category and segment, but the LOD expression was fixed at a less granular level of just segment. The LOD expression's values for each segment are replicated for each category within a segment in the view. In this instance, wrapping the expression in an aggregation isn't necessary, but since the view may change, it doesn't hurt to do so. When no aggregation is needed, because the expression's level of detail is coarser than the view's, the aggregation we specify is ignored. This arrow diagram illustrates the process schematically, showing the value of the LOD expression computed at a higher level than the viz, then being replicated to be displayed at the viz LOD. A final scenario is if the LOD expression's dimensions are entirely disjoint from the dimensions in the view. In this instance, an intermediate step is calculated behind the scenes, whereby the LOD expression's value is replicated for each combination of LOD expression and LOD of the view, then aggregated to the level of the view. This is also the behavior for disjoint nested LOD expressions, which will be covered in more detail in a different video. Include level of detail expressions compute values using the specified dimensions in addition to whatever dimensions are in the view. The include keyword will almost always yield LOD expressions that are below the viz LOD, and thus need to be aggregated up to be displayed in the view. Establishing what type of aggregation is performed on the LOD expression's results can be done in the calculation or on the pill in the view. Exclude level of detail expressions explicitly remove dimensions from the expression. That is, they subtract dimensions from the view level of detail. The exclude keyword will almost always yield LOD expression results that are above the viz LOD, and thus need to be duplicated to be displayed in the view. Tableau will default to show an exclude LOD expression pill in the view as ATTR rather than sum, because there's no aggregation happening other than what is defined inside the LOD expression's aggregate expression. Note that it is also possible to have an LOD expression match the viz LOD, in which case the LOD expression will seem to be an ordinary calculation, simply performing the aggregate expression. However, if the viz LOD changes, or the LOD expression is reused in a different view, the effects of the LOD expression can be seen. Some analysis questions can be quite elaborate. Nesting LOD expressions can help in these complex scenarios. To understand how nested LOD expressions will behave, it's important to know how they're evaluated. For example, what if we want to take this plot of how many customers have made a specific number of orders and find the average number of orders made? If we just bring out an average line, Tableau calculates the red line here, the average of the values on the horizontal axis. Is this really what we want? This average is adding the values on the axis and dividing by the total number of options, regardless of how many customers made each number of orders. Or rather, do we want the average across all customers of the number of orders made, considering the fact that 10 customers made 1 order and 117 customers made 6 orders? Nesting LOD expressions can help us do that. The initial LOD expression here gives us the number of orders made per customer. We can then take the average of that and a second fixed LOD expression at the scope of the table, that is, across all customers. Note that this average is smaller, as the volume of customers who made fewer orders is now taken into account. Let's leave that example and break down the idea of context for a nested LOD expression. Nested calculations inherit their dimensionality from the outer calculation. That is to say, the context for an inner calculation is defined by its parent, not the sheet. Here, we have two nested expressions, both of which would yield the same result. Why? Because the nested expression in the first example inherits its dimensionality from the outer calculation. That is, customer ID is included with country. This is the same thing as originally doing the calculation fixed at the level of customer ID and country, and then both of these averages are fixed to the level of country. The aggregation and replication behavior of a nested LOD expression follows the same rules as fixed. Replication, or aggregation, occurs to match the parent dimensions. If the inner calculation is more aggregated than the outer, the inner results are replicated to the outer calculation. If the inner calculation is more granular than the outer calculation, the results are aggregated by the outer calculation. In this case, the outer LOD has a finer aggregation than the inner, so the results are replicated from the inner to the outer. Then the overall results are aggregated down to the viz LOD, yielding the final results. R is a free, open-source statistical language. Tableau's R integration is intended for users who are familiar with R and know how to write the scripts and functions required and have access to R Server. Using R within Tableau is a straightforward process. Simply create a function that calls R and contains the R script. Tableau will pass the script and data to R, where the computation takes place. The results are returned to Tableau and can be visualized just like any other calculated field. Using R within Tableau requires a few steps to set up. First, R must be installed on the local machine along with Tableau Desktop. Next, RServe needs to be installed and initiated with R. RServe is a package which allows applications, such as Tableau Desktop, to use R without initializing R each time. Essentially, RServe is the connector between R and Tableau Desktop. To set up RServe, within R or RStudio, run the following. Install.packages RServe. Select a crayon mirror, and once the download is complete, run library RServe, ;RServe. Attempting to open a workbook with R functionality on a machine without R installed and set up within Tableau will result in an error that there is no RServe connection configured. In order to use R functionality in a workbook, that workbook must have an RServe connection. This holds both for locally shared workbooks and for workbooks published to Tableau Server. To set this up in Desktop, go to Help, Settings and Performance, Manage R Connection. The default settings of localhost and port 3611 are usually correct. RServe remains resident in memory even after the R console is closed and is still able to serve requests from Tableau. Publishing a workbook with R functionality to Tableau Server requires Server to have a connection to RServe. If multiple users need to access RServe simultaneously, RServe should be installed on Linux. RServe on Linux, unlike Windows, handles each user independently and does not allow users to overwrite others' objects. For more information on how to configure RServe using Tab Admin, please refer to the online help. One of the benefits of R is that there is a huge community of users who publish pre-built packages of functions, data, and code. Packages are downloaded and installed, and each session needs to load the package by using the library package command. Here, for example, this sheet should have a view. However, there's an error. An error occurred while communicating with the rserve service. When we click Show Details, we see an error in the library MV outlier. There is no package MV outlier. This lets us know we need to install that package in R. Back in R, go to Packages, Install Packages. Find MV outliers on the list and let the packages install. This can take some time. Once the packages are installed, load the library, Library MV outlier. Back in Tableau, the view renders properly. R functions are computed as table calculations in Tableau. In order to let Tableau know that a calculation needs to go to rserve, it must be passed using one of four functions: script boolean, script integer, script real, or script string. The argument for these functions is the R expression, followed by the Tableau reference parameters. For example, here is a function which simply adds 5 and 7. The R script using assignments is here. To communicate the same in Tableau, we'd start with script integer, because we know our result will be an integer. Then we'd enter argument 1 plus argument 2, followed by the assignment of the measures from Tableau. Our dataset simply contains two fields, 5 and 7. Because this is a table calculation, the fields must be aggregated, so we're using minimum of each of the fields. If we evaluate this calculation, we get 12. Here we have a view of profit by quarter of order date. We want to color code when profit was exceptionally high or low. R has a package for evaluating multivariate outliers, MV outlier. We have a calculated field here, which will ask R what values are outliers. To start, we have a Tableau if statement, such that if the script is 0, label it outlier. Otherwise, call it normal. Inside of that, we have the script real function, which lets Tableau know we're asking R for a real number. Now let's take a look at the R script itself. We call the library MV outlier package and run any functions from that package. Next, we establish the placeholder argument 1. Tableau is agnostic to the R script within the quotes. Because of this, it's often a good idea to test all scripts within R or RStudio before using them within Tableau. Finally, we have to let R know which measure. Here we'll use sum of profit to use for argument 1. Now let's bring outlier to color, and we can see we do have some outliers colored in orange. What if we want to see how our outlier analysis changes over time? As we drill down, we see the outliers automatically. Note that we don't have to modify or rewrite our calculation or R script. Tableau's functionality works seamlessly with R. Next, we'll go over an example of cluster analysis using R. This example uses Fisher's iris data, clustering 3 species of iris based on the dimensions of their petals and sepals. We've built scatter plots of these 4 measurements, and we want to cluster the points into 3 groups and see how well that matches the different species of irises. Let's take a look at the R script in the calculated field cluster. We're asking for an integer result, and the R script uses k-means clustering to create 3 clusters based on 4 measures. And the measures from Tableau are those petal and sepal measurements. When we bring clusters to color, we see the results of that cluster analysis from R visually. We also have the species information. If we bring that to color instead of cluster, we see that our analysis was pretty accurate. The details of these calculations can be examined by downloading the workbook from the video. Thank you for watching this calculations training video. We invite you to continue with the free training videos to learn more about using Tableau.